Hey everybody, it's Mrs. Harbin. Video notes 10-2. We're going to talk about what makes a chemical reaction happen. Okay, what drives it. Alright, we're going to talk about three main factors. Two factors that determine spontaneity, and one factor by itself that can tell us. So, what does spontaneous mean? Well, will the rock roll down the hill spontaneously? Yeah, if it gets started, it's going to go. Okay, if there's an earthquake, it's going to go. So spontaneous, when we're talking about a chemical reaction, is a process that occurs without outside intervention. It's like a natural process. Intervention. Okay, spontaneous reaction. Spontaneous reaction is going to be a chemical reaction that occurs without outside intervention. Okay, it's a preferred natural way for that reaction to go. Right? This pushing up a hill is not spontaneous. Rolling down a hill is spontaneous. Okay, not spontaneous. Down the hill would have been spontaneous. Okay, now don't get this confused. We've been talking about rate, but spontaneous doesn't mean fast. Doesn't necessarily mean fast. So fireworks are ignited for 4th of July. I bought a wrench in January, which becomes rusted by the 4th of July. Both are equally spontaneous. This is the natural process, natural occurrence. Without outside intervention, this is what happens to a wrench. Okay, this is the natural way for fireworks to go. Okay, both are equally spontaneous. Spontaneous doesn't mean fast, it just means the natural direction for a chemical reaction. Okay, now, spontaneous might have to require activation energy. What's activation energy? Maybe we'll get a little help in the background. Alright, so if you want to start a fire, look at that fire. Okay, you might have to light the firewood on fire, so you might need a spark. Why? Because you got to give the initial activation energy. Alright, you got to give it the climb. You got to give it the climb. Alright, but it is spontaneous for wood to burn. Okay, so that's what spontaneous means. It's a naturally occurring process. It might need activation energy, but it's a natural process. Okay, so what two factors will help us determine spontaneity? Well, one of those is called entropy. Entropy is the name of the term. Delta S is the symbol for it, and what it means is disorder or randomness. Okay, so what has more disorder? Well, if you have more gas, you have more entropy. If you have a solution from a solid and liquid, you have more entropy. If you have more particles, you have more entropy. If you increase the temperature or the volume of something, you increase the entropy. Nature favors having more entropy. Okay, so what is entropy? We'll think about it as disorder or randomness. Okay, the randomness of a system. More particles you have, more gas particles you have, more randomness you have, the more ways those molecules can be, the more disorder they have. Okay, so what has more disorder? This one. What has more disorder? This one. What is more random? This is definitely more random than that. High temperature is definitely more random than a low temperature. Okay, so here's a chemical reaction. Notice you have two gases and a solid turning into a gas. All right. This has less entropy because we have a gas and a solid. So this is delta S goes down in this one. That's a negative delta S. Okay. This solid and a liquid turn to aqueous, that is delta S increasing. So that's positive delta S. That's a favorable way. This is more random. Hot water to cold water is negative delta S because the temperature goes down. That's a decrease in randomness. Okay, sugar cubes ground up sugar, that's an increase. Positive change in entropy. Okay, entropy is disorder. This is more random. This is more random, so that means if it goes this way, it's a negative S. All right, this is more random, so this way is a positive S. This side's more random because we have, oh wait, I totally lied to you on that one. I'm erasing that one. You didn't hear that. We have solid and a gas. I should not circle it again. We have all gas on this side. So gas on this side is totally random. Totally random. Gas is the most random you can get. movement in every direction at all times. This is totally random, so this is a positive delta S. What was I thinking? I lied to you, but I changed it. All right, no more lying from Harbin, promise. Okay, so just to review, what is entropy? Entropy is delta S. What does delta S mean? Or what does entropy mean? It means the system gets more random for positive S. The system gets less random for negative S. So think about what the particles are doing. Solid particles are close together, so they're ordered, so that is not random. So that's a decrease in entropy. Liquid particles are together, but they're moving around each other. That's more entropy. Gas particles are totally random. That's the most entropy. Okay. Hey, what's this? This is something we already talked about. It's enthalpy. It's heat. It's delta H. Okay. Endothermic reactions have a positive delta H. Exothermic reactions have a negative delta H. And then if you're looking at a chemical reaction, you can look at the side of the arrow. So positive delta H would be on this side, negative delta H will be on this side. So why did I bring up enthalpy again? Because those two E words are the two driving forces of chemistry. Those two E words, entropy and enthalpy, randomness and heat. Change in randomness and change in heat will help us determine if a reaction is favored in nature. So what is the natural order for entropy is more randomness. So nature wants positive delta S and negative delta H. What is favored? High or low energy? Low energy is favored. Chill is favored. That's a negative delta H. What is favored? Comb hair or messy hair? Combed hair or messy hair? This is nature's way. You have to fight it every day, right? So positive disorder. Whoa, look at that order. Order, disorder. Okay? So these are nature's favored factors for predicting whether a reaction is going to be spontaneous or not. You need to look at two factors, the heat and the randomness. Negative heat and positive randomness mean it's going to be a spontaneous reaction. How can we look at both of those two things together? We can look at something called delta G, which is Gibbs free energy. Here's the mathematical equation for calculating delta G, and look what's in it. Oh, look, some enthalpy. Oh, look, some entropy. So what's this T? T is temperature. Temperature. And it has to be in Kelvin. All right? So, Gibbs free energy is, if you know Gibbs free energy, you already take into account the H and the S, so you know whether a reaction is spontaneous. Because if a reaction releases free energy, then it's a spontaneous reaction. If delta G is negative, the reaction is spontaneous. If delta G is positive, the reaction is not spontaneous. If delta G is 0, we have a situation called equilibrium, which is our next chapter. So actually, equilibrium means the forward reaction and the reverse reaction are happening at the constant rate. Okay. What is Gibbs free energy? Free energy is energy free to do work. So all of the other energy is tied up in breaking bonds and making bonds and yada, yada, yada. Free energy is the energy after talking about enthalpy and entropy that's left over to do work outside of the chemical reaction. It goes out into the world. Okay, so how do we calculate delta H? Well, here's a reaction to remember. A mathematical equation to remember. If you want to calculate delta H of a reaction, you have to add up. This is sum. Add up all of the delta H's of the products and subtract the sum of the delta H's of the reactants. Okay. I'm going to tell you about, make sure, multiply by coefficients. Multiply by coefficients when you're doing this. Okay. Here's some delta H data. We know about ammonia. We know about oxygen. But wait, we don't know about oxygen because it's not in this information here. So the delta H of formation, that's what these are, how much energy it takes to form each compound. Delta H of formation for elements in their standard state. You should write this down. Elements in normal state. Normal state equals 0. Okay, so NH3 is in this table. NO is in the table. And H2O is in the table. Why isn't oxygen in the table? Because oxygen, O2 gas, is the normal state of oxygen, so it's assigned a value of 0 for its natural state. Okay, so now how do we calculate the delta H for this reaction? we have to get the sum of the products. Okay, so we take 4 times the negative 46 plus, we're getting the sum, we're adding them up, 6 times negative 286. That's going to be the sum of the products. Remember, it's products minus the sum of the reactants. So let's see what the reactants are. We have NH3. Oh, wait a second. Did I mess up? Wow, this is not going well for me today, but I'm going to fix it. NO is 90. All right, so 4 times 90 plus 6 times negative 286. Those are the products. All right, so I summed those. I multiplied, and then I have to add that up. On this side, I have a coefficient of 4. And so I have to multiply that by negative 46 because that's the heat of formation of ammonia. And then 5 times 0 is 0. Okay, so what does this give me? Remember, this is reactants. This gives me negative 1,356 for the products minus negative 184 for the reactants, negative plus, and I get negative 1,172. Now you might be wondering what units that would be. That would be kilojoules. Okay, so the delta H for this reaction can be calculated using information like this. Oh, look it, here's a table. This is a table of delta H's and delta S's. So you'll be able to get one of these tables and use it accordingly. Dun, dun, dun. Okay, hey, wait. How can we calculate delta S? Same way, just a little different. So this is sum of all of the products and the sum of all of the reactants, and then it's products minus reactants. So let's look at this table. We need silver chloride. Where's silver chloride? Where's silver chloride? The delta S is negative 0.096 kilojoule mole kelvins. Okay, so we got to do products. So 2 times 0.096 from the table. Okay, and there's only one product, so that's product minus the sum of the reactants. So 2 times silver. Silver is 0.0426. So how did I get that? Let's see. Silver. Okay. Plus, remember, I'm adding them together before I divide. Chlorine, 2.223. Okay. So what we get, and that's a reactant, so it's products minus reactants. We're going to get 0.192 minus 0.3083 equals negative, wait, that doesn't look right. Yeah, negative 0.1163, and then kilojoules per mole Kelvin. Okay, now since we multiplied by moles for those, the moles kind of cancel there, and we're left with kilojoule Kelvin. All right, kilojoule Kelvins there, because this was 2 moles. This was 2 moles. We multiplied by this, which is per mole. All right, so delta S is calculated the same way as delta H from using information. Okay, so now we have to know 3 formulas to calculate. This just means the sum of. So add them all up. Okay, now we could calculate. So let's go back and see if we would have predicted this to be increase or decrease in entropy. Okay, so this is. So let's just go to what's going on here. Okay, so now we have 3 calculations that we can do to figure out. Okay, so here's a delta G calculation. If I tell you the system has a temperature of 298 Kelvin, an enthalpy change of negative 223, and an entropy change of 0.035 kilojoules per Kelvin, what is the Gibbs free energy? Okay, what is that? Is this a spontaneous process? So let's see. So delta G equals delta H, negative 223 kilojoules, minus T, 298 Kelvin, times delta S, 0.035 kilojoule kelvins. Okay, kelvins cancel with kelvins. All right, so we have negative 223 minus 298 times 0.035. So we have negative 223 kilojoules minus 298 times 0.35. So let's see, on clear. 298 times 0.035, enter. It gives us 10.43. So plus the negative, so we're going to have negative 233.43, and that is going to be kilojoules. Why? Because kelvins cancels kelvins, this is kilojoules, this is kilojoules. So the Gibbs free energy is negative 233.43. What does that mean? Well, remember that delta G equals negative is spontaneous, because that means the free energy, which is the delta G, is released into the environment so it can do other work. Alright, so we can predict things. Delta H is heat, delta S is randomness. Alright, randomness. So, delta H. If delta H is negative, that's favored by nature. Delta S is positive, more randomness, that's favored by nature. So guess what? If we plug in a negative sign there and a positive sign there, this is going to be always negative. This is going to make delta G negative. So that's always going to be spontaneous. But if this is not favored by nature, that's endothermic. Decrease in randomness is not favored by nature, so that will never be a spontaneous reaction and will always have a positive delta G. Hey, what if this is favored by nature? Yay! But it gets less random. That's not favored, so maybe it's going to be spontaneous. So we'd have to do the math calculations for that one. Hey, if this is not favored by nature and this is more random, then we got another maybe. So we'd have to do some math. Alright, so you might be thinking, hey, Mrs. Harbin, you told us about when delta G is negative, it's spontaneous. When it's positive, it's not spontaneous. But what if delta G is 0? Well, then the system's going to be at equilibrium. And that means that the forward reaction is happening, the reverse reaction is happening, and they're happening at the same rate. So it doesn't look like anything's happening, but it is. Wow, we're going to talk about that later. Okay, so to review, enthalpy is heat, delta H. Entropy is disorder or randomness, delta S. Okay, random mess. That's funny, random mess, randomness. And they help us determine whether the reaction is spontaneous. We have to calculate H and S. Remember to do products minus reactants in tables. Then we could calculate G if we know either of those and the temperature. Entropy is disorder and often found by counting gas particles. We'll practice that. And then Gibbs free energy is negative, means you have a spontaneous reaction. Alright, just remember that activation energy is the climb. It's from the bottom, from where you start to the top of the hill. Okay, activation energy. Alright, just keep pushing on. Alright, peace out, kids.